Hello again, this is Dr. Jenkins. This is our first video on water and fluid balance. Now we're about to enter a pretty big block. So I call it here Module 9 because I believe it's Chapter 9 in the Jenkins text. But this module, don't let my yawn make you feel less excited. I'm sorry about that. This module is going to cover water and fluid balance, and it's also going to cover thermoregulation. Okay, so we have a lot to cover, which means that I'm going to move a little bit more quickly through the material, but as always, I'm going to be underlining or putting a star or writing down what's most important. So just focus on what's most important. Here's our outline for the water and fluid balance chapter. I don't know why I just all of a sudden started to yawn when I sat down to do this, but I am sorry. Okay, so we're going to start really basic. We know that water is, okay, can I go out here now? We know that water is H2O, so it's 2 hydrogen molecules and 1 oxygen molecule. It kind of looks like an upside down Mickey Mouse face to me. You don't have to know the specific structure though. We do know that it is very abundant in the body. And we may remember it is one of our macronutrients, right? Oh, of course it is. So we had carbs, carbohydrates, fat, protein, and these are the chapters that we've just completed. So it just is very logical that we're going to next cover another macronutrient, which is water. And that means that we need to ingest a lot of it. I'm going to point out some of the functions for you to know. We definitely rely on water for transportation in the bloodstream. We rely on water to help us sweat and maintain our body temperature. We know that water can be a lubricant. Think about the fluid in your joints. We have moving parts where there's a lot of friction. So we have water that makes up synovial fluid to reduce friction. Universal solvent. What this means is things dissolve in it. So in the body, particularly in the bloodstream, water is a universal solvent. That just means that a lot of things dissolve in it. Think of sodium or salt. That's a good example. Sodium is able to dissolve in water. And that's a really important chemical property. And we'll leave it at that. Review those functions. Okay, if we look at our composition of water in terms of our body, it is pretty darn big. So I would say for most people, about 50 to 60% of our body is water. And this is why hydration, maintaining enough water for what our body needs, is so important, okay? So you should know that range, about 50 to 60% of our body is water. The rest here you don't need to know. So if I don't talk about it, you don't need to know it. Okay, now we're going to get a little bit more into the science. And if we talk about that distribution of water, I said that it was about 50 to 60% of our body. It's usually about 4 to 6 liters worth of water in our body at any given time. I want you to know this percentage. You don't have to know the actual liters, but I'm just trying to give you a ballpark in case you're interested. So let's just take right in the middle 5 liters. Let's say a given person has about 5 liters of water in their body, in the bloodstream, in the fluid around their heart, in the fluid in their joints, etc. Well, where do we store that 5 liters? And this is actually a pretty important thing to differentiate, especially when we get to thermoregulation. because when we need to sweat, which means that we send water to the surface of our skin, and then that water evaporates off of the surface of our skin, and that evaporation has a cooling effect. In order to do that, we've got to shift water around in order to be able to send it to the skin. And we shift it between these compartments, is what I meant to get at. But let's just keep it simple to start. About 2/3 of all of our water, so if we have 5 liters in our body at a given time of water, about 2/3 of that 5 liters of water is stored inside of the cells, or in the intracellular fluid. So in this picture, we have cells. They could be any cells you want. They could be muscle cells, they could be liver cells, you pick. But we have a lot of water. This is why the cells are colored in blue, because there's a bunch of water in our cells. Our cells are really robust. They're puffy because we hold a bunch of water in the cells. Which means that the remaining third or so of water is stored in outside of the cells. So an example of that could be outside of the cells could be in the bloodstream. So there's some water in the bloodstream. There's also some water in between the cells, or interstitial fluid. You don't have to know this breakdown, but you should know that about 1/3 of our water is stored outside of the cells in what we consider to be the extracellular compartment, which includes our bloodstream because it's outside of the blood cells. And most of our water, 2/3 of it, is shoved into our cells. I mean, pretty interesting, at least to me. Now, when we talk about water, we would be doing ourselves a disservice if we didn't also talk about electrolytes. Just a fair warning, I'm about to get on a little bit of my high horse, or one of my little soapboxes. Many people talk about electrolytes like they know a lot about them. Well, I drink Gatorade because I need electrolytes. But not many people really know what the hell they are and why they are so important. And actually, is the electrolytes that we're getting from Gatorade what we need? Well, this is why you're here, folks. I'm here to help answer these very important questions. Let's talk about what electrolytes are in terms of our body. In our body, electrolytes are charged particles, and we'll see that because when we write an electrolyte, it either has a plus sign with it or it has a minus sign with it, sodium or chloride, right? It's a charged particle, and it's a charged particle that has the ability to carry a current. And I know that's a little bit abstract, but it's just that it's not only a charged particle, because we have other charged particles, like iron. When you write out iron, it has a minus sign beside it. That's a charged particle, but it is not an electrolyte, because it is not a charged particle that has this ability to carry a current. And the reason that this ability to carry a current is so important is because these electrolytes contribute to really important things. Okay? Anytime that we have a nerve impulse in our body, anytime that we contract our muscles, it is because of these electrolytes. So in other words, because of, and without getting too much into the weeds here, I have a hard time controlling myself because I get so excited about all this. If we take potassium and sodium, for example, these are both electrolytes. These are our two most common ones that we talk about. Potassium and sodium are constantly moving into and out of the cell. And that movement, just imagine if we move a bunch of things that are positively charged in one way, it influences the electricity of everything around it. And if we move around these ions in a certain, these electrolytes, if we move around these electrolytes in a certain way, we can generate an electrical current. And that electrical current is exactly what a nerve impulse is. So here's what I'm telling you, folks. We would not be able to send a nerve impulse, which is an electrical current. We would not be able to send a nerve impulse without an appropriate distribution of these electrolytes. We also need them for muscle contraction. In muscle contraction, not only do we rely on potassium and sodium, we also rely on calcium. Okay? Without these electrolytes that carry a charge and have an ability to carry a current, we would not be able to create a nerve impulse. We would not be able to generate a muscle contraction. These things are also true, but for right now, you don't need to know them. See, look, we've debunked electrolytes. Electrolytes are a charged particle that carries a current. And they're important because they allow our body to make nerve impulses and muscle contractions. We can manipulate the movement of these charged particles that carry a current in such a way to actually generate an electrical signal. That's pretty cool. Okay, I'm showing restraint. I'm moving on, even though I really want to keep talking about it. Okay, I'm going to ask that you will become familiar with two electrolytes, sodium and potassium. They are both positively charged. You don't need to know these normal amounts. It's just there, FYI, if you're interested. What I do want to point out, however, is where we find most of these. We tend to find a higher amount of potassium inside cells, whereas we tend to find a lot of sodium outside of cells. And that's really important. If I go back to our slide about water distribution, this was listed here. We have more potassium inside the cell. So imagine we have more potassium here versus we have more sodium outside the cells. And it's really important that one is on one side and one is on the other, because it allows us to have a membrane, which happens to be the cell membrane, through which we can move these electrolytes in and out to generate a current. Okay, so sodium is found in higher amounts outside of the cell. Potassium is found in higher amounts inside of the cell. I already said this, but let's say it again just to make sure that we're clear. Both water and electrolytes are constantly moving into the cells and constantly moving out of the cells, because our body is going to shift the water to where it's needed. And then as we bring in more water, we're going to be able to replenish the water stores. So it is absolutely vital that we're able to move not only the water, but also electrolytes into and out of cells, into and out of the bloodstream, constantly moving. Okay, so now that we've established what the functions of water are, we've established how much water we have and where we find that water, let's talk about water balance. Just like with calories, overall calories, and just like with carbohydrates, fat, and protein, you want to have a balance. You want to bring in enough fluid to match what you're losing. The easiest example of this is sweating. I'm recording this in July, and it's been a pretty hot summer. So in the heat, we're going to sweat more, and when we sweat, we lose fluid. So instead of losing just a normal amount of fluid, now I'm losing a bunch more. So if you lose more fluid, you better be drinking in water to equal it out. And it can be a hard thing to do because this is indeed a hard thing to measure, particularly in athletes. It's really hard. It's almost impossible to determine how much exactly someone has sweated, especially out in an actual game or practice. How do you know? Some of it is, some of that sweat is evaporated into the environment. Some of that sweat gets soaked into your clothing. It's really hard. So I'm going to be talking about some strategies to try and figure out how much athletes need to hydrate. But it's hard, okay? All right, so I want to break this down. I want you to know the 3 ways that we bring fluid into our body. We're going to be very simplistic. We're going to talk about what are the ways that we bring in fluid, and then what are the ways that we get rid of fluid. And that'll help us to better understand this balance, right? We'll talk about ways in which we bring in water, then we'll talk about ways in which we get rid of it. This picture is not from your textbook, I don't think. It's from a different textbook that I've used. I just really like it because it's simple. All right. The majority of water that we bring in comes from drink. You do not need to know an exact number, but you should know that this is how we bring in most of our water. So most of our fluid comes in this way. Everyone should be drinking their water. Yes, yes, yes. To a much smaller degree, we bring in water through food. There's water in food. Some foods have a higher water content than others. Fruits have a high water content. If you take it, for example, eggplant has a very high water content. But even other foods has a little bit of water in it. And the way that we bring in the least amount of water is something we call metabolic water. And this is water that is a byproduct of chemical reactions. Just like we often need water to carry out a chemical reaction, often water ends up being a byproduct or is released as a result of a chemical reaction. It's a smaller amount, but it is indeed there. This is an average, but you don't need to know these numbers. Don't worry about that. Just know the 3 ways in which we bring in fluid, which one is the way that we rely on most, and which is the way that we bring in the least amount of water. Now, fluid loss is a little bit more varied. We're going to talk about 4 ways in which we release fluid. The biggest way that we release fluid at rest is through urine. For most people, our normal urine output for a day is about 1 to 2 liters, and that's quite a bit. We can release fluid through the skin as sweat. This can become our biggest loss during exercise. It depends on the person. Depends on what they're doing, their intensity, their duration, the atmospheric conditions, the temperature, the humidity, the altitude actually also affects also affects our fluid balance. So urine is the biggest means through which we release fluid at rest. Sweat can be the biggest way that we release fluid through exercise. We release smaller amounts of fluid through our poop, and we do actually release some fluid through breathing. So when you breathe out, there's some moisture droplets in your exhaled air. It's not a very big way that we lose water, but it is indeed a way. All right, so make sure you know these 4 ways that which we can lose fluid, and which can be the biggest means of fluid loss at rest and exercise, and then which 2 are smaller avenues of fluid loss. The goal, of course, is to be balanced. This, of course, changes on the situation. Exercise. It can also be changed. It can also change depending on illness. I mean, if you're sick, it's much more easy to become dehydrated, so you better drink in more. So it's always changing. All right. It wouldn't be a science class if we didn't talk about regulation. How do we regulate this fluid balance? If we know that water and electrolytes are always moving into and out of the cell, if we know that we're constantly needing to change how much and what ways in which we release fluid, well, what is it in our body that makes those decisions for us? Well, let's first talk about the hypothalamus. The hypothalamus is a region in the brain, and this is the regulatory center for thirst in your brain. You may hear it sometimes called as the brain's thirst center. So any type of messages, any type of sensory messages from the body that go up to the brain relating to fluid automatically go to the hypothalamus. When your brain has to make decisions about if it needs to tell the body to sweat more, for example, that message is coming from the hypothalamus. This is the regulatory center for thirst in the brain. You don't need to know about the how. And then we also rely on a series of hormones. And these hormones are chemical messengers. In terms of fluid and hydration, there probably is no bigger hormone to discuss than antidiuretic hormone. I'd like you to know this hormone. You may have heard it. It's usually abbreviated as ADH. Antidiuretic hormone, ADH. ADH is a hormone. It's actually released from the pituitary gland up in your brain. It has its action at the kidneys. You don't need to know either of those things, but I'm just putting it out there. What ADH tells the kidneys to do, and I'm going to try and use very simplistic language, tells kidneys to retain more water. Make sure you know this function. So I guess you do need to know that its target organ is the kidneys. When your body releases ADH, it tells your kidneys to retain more water, which means that you're peeing out less. So instead of a lot of that fluid being lost through urine, your body is instead retaining it. And this is a huge way that we can regulate fluid. And by the way, the signal to tell the body when to release ADH comes from the hypothalamus. So they work together. You can imagine if it's really hot out, maybe you're not drinking as much, your body is going to release ADH. So if your body is in a condition of dehydration, for whatever reason, you're not bringing in as much water as you need to replace the water that you're losing. So if you're dehydrated, your body is going to release more ADH. Tell the kidneys to retain more water. The opposite would be true. If you have already just drank a ton of water and you actually are well hydrated, maybe even a little bit too hydrated at a given point in time, your body will inhibit release of ADH. And by inhibiting what usually tells your kidneys to retain water, by inhibiting what usually retains, your kidneys will pee out more. So that's how we have a push and a pull. We either release more or less ADH. Good stuff, isn't it? Here's a nice schematic if you want to see, like pretty much anything else in the body, we operate on an equilibrium where things should be equal, right? But instead, if things are not equal, here we have a problem where now we have a condition of dehydration. So instead of us having a nice balance where we want to be, which is right here, we have dehydration. We're losing more water than we're bringing in. Your body works on a negative feedback loop where something senses that, and then that dehydration, and then will communicate to the hypothalamus, hey, our body's dehydrated. Your hypothalamus will respond to do something that will bring hydration back up. And you can see it's a negative feedback loop. So whatever the initial problem is gets corrected. You don't need to know the schematic. It's just there just in case. Okay. Now, there's a lot of things that affect that fluid balance. I've already alluded to this. Let's get into some of the details. And a lot of this, folks, is common sense. So sometimes you can just try not to outthink the room. There's the KISS principle, keep it simple. When you exercise, you're going to have more fluid loss. Duh, right? Because you're sweating more. You're also breathing out more. You know, there's water droplets in your exhaled air. So exercise leads to more fluid loss, which means that to fix that, we have to drink more. Heat, humidity, both of these together, heat and humidity, increase. Oh, wait a minute. You know, I spoke too fast. Let's take this back. Okay, let's start with heat. Heat will also increase fluid loss because if it's hotter, you're going to need to sweat more, so you're losing more fluid. Humidity. We're going to talk about humidity more when we get to the thermoregulation chapter. Humidity can actually make it more difficult for your sweat to evaporate, which means that you may not have as much fluid loss. Your body's going to be trying to get rid of fluid through sweat, but because of the humidity in the air, it's more difficult for that sweat to evaporate. Don't worry about this now because we'll talk about it. Cold can affect fluid balance a little bit, but I'm not going to give you a specific there. It really depends. Obviously, you're not going to sweat as much when it's cold, but I do think some athletes get caught up in a trap. Oh, it's cold out. I'm probably not sweating that much. I don't need to hydrate really at all. Well, that's not true. Because even if you're exercising, you're still going to have at least more fluid loss to a certain extent. So don't think that just because it's cold, you don't need to think about hydration. Altitude can also influence our fluid balance. You don't need to know it, but if you're interested, altitude naturally, even if you're at rest, even if you just take a hike up to high altitude or you fly to Denver and you're there for a while, altitude leads to dehydration. So it leads to less fluid loss. don't need to worry about this for us because altitude leads to dehydration. And this is something that is not talked about as much. People talk about acclimatization or the need to get used to altitude as athletes, but they don't often talk about the need to drink more, because indeed going to altitude, even at rest, is a dehydrator. Gender, as a whole, males tend to have more fluid loss. Not always, but if we were to sample a large sample of the population, we would find this to be true. Compared to each other, men will lose more fluid. And that has mostly to do with, first of all, how they thermoregulate. But aside from that, it has more to do with having more surface area of their skin. So if you have more surface area of the skin because they're bigger and taller, men tend to lose more fluid. Age. I want to point out this difference. I'll talk about this more in our chapter on thermoregulation. Children cannot sweat as well, whereas adults are able to sweat better. And this can influence fluid balance, obviously. I don't want to write down more or less fluid loss because it doesn't necessarily mean that children need less fluid than adults. I mean, per body weight, yes. But I think it's an important distinction. Children do not have as well developed sweat glands. They have less surface area of their skin with which to be able to evaporate the sweat from. And I'll say this again when we get to the thermoregulation chapter. You know, someone's coaching a Pop Warner football team, and it's a 20-year-old male, and it's hot out, but he's okay. Yet the kids, they cannot sweat as well, so they're not going to be able to handle the heat as well. So you need to give kids more water breaks, more rest breaks. It's not because they're pansies, you know. I understand the idea. Some people want to make them tough. But if you understand the science behind it, you could definitely be dehydrating these children. Okay, body composition. I'm not going to ask you anything in terms of this right now. We'll talk about it more next chapter. Fitness level, I'm not going to talk about this now either. But if you want to know fitness, as you get more fit, you'll be better able to replenish your fluids. So you won't need as much sweat to be able to maintain the right body temperature. But don't worry about those two for now. Okay, I'm going to stop there, and then we'll pick this up in the next video.